Hello everyone, I hope you're doing well. So in this video, we're going to discuss Geeks for Geeks problem of the day, and today's problem is find maximum equal sum of 3 stacks, right? And it is a medium level problem. So if by the end of this video you feel that it was helpful for you, then consider dropping a like on this video, and don't forget to share your thoughts in the comments or any general thing you would like to share, because your engagement with this particular video really helps the YouTube algorithm to understand that it was actually helpful for you, and it will be able to reach more people like you who want to keep solving new problems. So this particular problem might seem a bit tricky at first glance, but if you try to break down it into smaller problems, then it becomes much easier, right? So let me just take this sample test case and explain you with an example what the problem statement says. So here we have three arrays, right? Here we have three arrays, and basically they are in the form of a stack. So 4, 2 and 3 is like this, and then we have 1, 1, 2 and 3, and then we have 1 and 4, right? So what we essentially do is we check the sum of all these three stacks. So currently the sum is 4, 5, 6, 7, 8, 9, right? Here the sum is 3, 4, 5, 6, 7. Here the sum is 5. So what we essentially have to do is we have to remove some elements from the top of these stacks, right? And we have to remove them in such a way such that the remaining sum is equal in all of the three stacks. So for example, if I remove 4 from here, so if I remove 4, this will become 5. This is 3 plus 2, 5. If I remove these 2 from here, 1 and 1, the overall sum will reduce by 2 and this will become 5, and this is already 5, right? So you see that the sum is now equal in all the three stacks, and hence the answer is 5. So you have to make sure that the remaining sum that you get is the maximum among all the possible ways, right? So you have to also maximize this particular sum. Otherwise, if you don't find any sum, you can always remove all the elements from the stack, and the sum will become 0 obviously in all the three stacks, right? So in the worst case the answer can be 0, and in any other case the answer will be greater than 0, right? So this is our whole question. Now if you look at it carefully, basically what is the sum of this particular stack, right? If all the three elements were there, the sum is 9, right? And if only two elements were there, the sum was 5, and if like the last element was there, sum is 3, right? So basically this is the suffix sum array, right? This is the suffix sum array of the of my first array or the first stack. And if I write the second one, it is going to be 3, then 5, then 6, then 7. It is also the suffix sum array. So my suffix sum array of the stacks is representing what if this particular element is present in the stack, what will be the sum of the whole stack, right? If this is the topmost element, what will be the sum of the whole stack? Similarly for 1 and 4, the suffix sum will be 4 and 5 like this, right? So if only starting from this particular element is present in my stack, what will be the sum of my stack? This is what my suffix sum array gives, right? Now you must observe one thing that you essentially have to find in this particular array. Now essentially have to find the greatest value that is present in all of the three arrays, right? For example, there was 5 here, right? So 5 is present in all of the three arrays, right? And since it is the greatest value, it is going to be my answer. If there was some value x, let's say if there was some value x like this, which was present in all of the three arrays, right, then my answer would have been x. So I just have to find the greatest value that is present in the suffix sum array of all the three arrays. Now what I have to do is, let's assume that there are some pointers like this, right, denoting that the top of the stack is currently the first element in these three arrays, right? Now what happens, like in a case when this particular element is greater than either this one or this one, right? If it is greater than both of these, then definitely I will have to remove this element from the top of the stack. But what if it was greater than only one of them? So let's say this was 9 actually. Let's say this was some other value other than 1. Let us just assume this for now. And let's say this value was 5. So if this value is 5, now this particular 9 is greater than the last 5. Can I increase this particular 5 to make 9? I cannot do it. So 5 can never be my answer in this particular case, right? So if the value is greater than even one of those other values, I'll have to decrement my pointer. So what I essentially do is, now I'll just move my pointer to the next pointer, and now I know that my remaining sum is 5, right? So if this particular value 5 is greater than any others, I'll have to decrement my pointer, right? And at each step, I will have to do this like decrement thing for all the 3 arrays, right? So I just decrement my pointer, or you can say increment also. You actually moving to the right, right? So you can move the pointer to the right in the first array. Similarly, in the second array, if this value is greater than the other two values, so now this value is 9 here, and this value has become 5 here, right? So this is 5 here, right? So 9 is greater than 5. That is why you decrement the array. In the next iteration, this 6 will again be greater than these two 5s. Then you will move your array here, pointer here, right? Now you see that all the three values are equal values, right? So as soon as you find all the three values to be equal, you can just return this as your answer. Now you might wonder, like the space complexity mentioned was O of 1. The space complexity was mentioned as O of 1, then why are we using three different arrays? So a very simple observation like will lead you to this particular conclusion that you don't even actually need these three arrays, right? Let's say you were at this position. You were at this position. Now, how to transition from this state to this state? So this is exactly like optimizing DP states, right? Whenever I have a DP transition, DP of I is depending somehow on DP of I minus 1, right? I know how it is depending, right? So these two are interdependent. So I always knew that I can always derive DP of I from DP of I minus 1. So instead of having the whole DP array, I just had two DP states, DP of I and DP of I minus 1, and I was able to just form every DP of I from DP of I minus 1, right? Similarly here also, instead of maintaining the whole array, if you just have the first state, from the first state you can derive the second state by decrementing this particular value. From the second state you can derive the third state by decrementing this particular value. So this array thing or the suffix array thing was just for your understanding, and instead of taking the whole array, you can derive the next pointer by decrementing the value at position of I in the original array, right? So the transition is very easy. You can go from 9 to, this was not actually 9, this was 7, right? So you can go from 7 to 6 by decrementing 1, then from 6 to 5 by decrementing 1, then from 5 to 3 by decrementing 2. So basically what you'll have to do now is, let's say you have some arrays, this is A plus B, let's say this is A plus B plus C, right? This will be your arrays. This is C and this is C plus D. Let's say these are the two arrays. You have to check whether these elements are greater than each other or not. If the first element here is greater than this particular element, then you have to increment this pointer, because this sum will never be possible now, right? Since I want to find the greatest element that is present in all of these three arrays, I need to increment this pointer, because this sum is never possible. So I check whether A plus B is equal to C plus D or not. If it is equal, then this will be my answer. Otherwise, if A plus B is greater, I increment this particular pointer. If C plus D is greater, I can increment this particular pointer. This is how you can easily do it using suffix arrays. Now the thing is, you want to do it in O of 1 space, so you can easily optimize this whole concept as using only one pointer, because from A plus B plus C, from this particular state, if you want to go to A plus B, then you just need to remove this particular last part, and this part will be present in the array position, right? So you can just do A plus B plus C minus C, right? So we'll get from this particular state to this particular state. So don't even have to maintain the whole array, you can just make simple transitions, right? So this will be the whole base idea of this particular problem. Now let us have a look at the code, how we did it. So basically I have created three variables x, y and z, and I have calculated the last element that I have. So last element means the sum of all the values, all the suffix values. So you see that the last element here, that is this one, will have the sum of all the values 4 plus 2 plus 3, right? So that is what I am calculating for all the three arrays separately in x, y and z variables, right? Now I initialize three pointers I, j and k, which will traverse through each of the vectors independently. Now I check if all the values are equal, if x is equal to y and y is equal to z, I can just directly return this particular value, right? Return x. Now I check whether x is greater than y. So if the value in my first array is greater than the value in the second array, or the value in the first array is greater than the value in the third array, right? So if it is greater, then definitely it is not possible to find this particular value x, right? Because we will never be able to form this answer. So I just decrement the current value from x and increment my I pointer. So you see I am doing post increment. right? So that is why I'm doing x minus is equals to s1 I plus plus, right? So this will decrement the value at the current position I and it increment my I point. Similarly, I do the exact same thing for y and z, right? So I'm just trying to match both x, y and z to their equal levels. If even after executing all of these loops, even if one of them is empty, right? So if I is not less than n1, that means we have exhausted all the elements in the s1 array, right? If one of them, even if one of the condition is satisfied, that means we cannot form any common answer, and that is why I return 0 at the end. So this was the solution of today's problem of the day. Now let me just quickly submit this and show it to you that this particular approach works, and you see that it passes all the test cases. So this was all about today's problem of the day. I hope that you guys were able to understand the solution. If you guys did, then consider dropping a like on this video and don't forget to subscribe to this channel. I see a lot of people who watch these videos have not subscribed yet. So if you're one of them, then consider subscribing. It's always free of cost and you can always unsubscribe if you don't find the videos interesting later. So share this channel with your friends. Until the next video drops, keep coding, stay safe, bye bye.